the algorithms that we have studied so far, we never talked about channel failures or channels coming up or node failures, etc. So, we will start with this algorithm which is called the net change algorithm. It is also another version of a wave algorithm, and we will make the following assumptions about this algorithm: that the nodes know the size of the network, okay, the size of the network, namely the number of vertices in the network is known, that is n. The channels satisfy the FIFO assumption. So, when packets are sent along the channel, they are received in the same order. Nodes are notified of failures and repairs of the adjacent channels. So, when a channel goes down, then the nodes which are at the two ends of the channel know that this channel has gone down. Similarly, when the channel is repaired, then the adjacent nodes come to know that this channel has come up, okay. And the cost of a path equals to the number of channels in the path. So, we are not going to talk about weights of the channels anymore. The weight of each channel is 1. So, we are going to route packets based on the minimum number of hops, okay. So, shortest path will mean the minimum number of hops to the destination. There are some requirements for this algorithm to work. The first requirement is, if the topology of the network remains constant after a finite number of topological changes, then the algorithm terminates after a finite number of steps. So, essentially what this means is that this is an algorithm which deals with failures of channels from time to time. So, it is receptive to the changes in the topology of the network, but at the same time, if the topology keeps on changing continuously, then obviously it is not possible for any distributed algorithm to come to a steady state and still guarantee that the packets are routed along the minimum hop distance. Obviously, we know that. So, we therefore assume that between topological changes there is sufficient amount of time for the algorithm to settle. Now, the algorithm guarantees that if that amount of time is given, then it is going to settle down into a set of routing tables at the nodes such that packets are routed along the minimum hop measure, okay. That is the guarantee of the algorithm, given that the topological changes are not going to happen continuously. So, you are going to have some time at least when the algorithm can finally do its computation and settle. Then after that, again if the topology changes, the algorithm will again run, and again it is going to bring the situation, the system to a stable state. Now, when the algorithm terminates, then the algorithm guarantees that the tables NBUV satisfy that if V equal to U, then NBUV is equal to local, that is, if the packet has arrived, then it will be delivered locally. If a path from U to V, where V is not equal to U, exists, then NBUV is equal to W, where W is the first neighbor of U on a shortest path from U to V. So, this is what the algorithm will guarantee, that the packet is routed to the neighbor along the shortest path from U to V, and if no path from U to V exists, then NBUV will be undefined. So, that means that the packet will simply be discarded, because it will be found that it has arrived at a node or has been generated at a node from which there is no way to reach V, okay. This is what are the requirements of the net change algorithm. Now, let us look at how the algorithm works. So, the algorithm is going to work, so you understand how the Chandi Mishra algorithm works. So, what happens there is that whenever there is a change in the network, what the net change algorithm will do is that the nodes which are adjacent to that change, they will recompute their distances and then they will broadcast their distances to their neighbors in turn will recompute the distances, and this is going to continue until everybody has settled down again to their minimum distances. Okay. Now, each node is going to maintain the following set of data. For a node u, nei u is the set of neighbors of u, okay, just like we had before. Du is an array and duv will contain the estimate of the distance from u to v, okay, like before, like in Chandi lamp Mishra's algorithm. Duv will denote the distance from u to v, that is the estimate that u stores about its distance to v. Okay. NBU is an array of nodes. NBUV is the preferred neighbor for routing packets to v. Okay. Again as before, no difference with before. The only new data structure that is coming here is every node also maintains a array ndis u wv, and this estimates the distance from neighbor w to some distance, some destination v. So, let me reiterate once again what are the things that we are storing in u. We are storing du v, which is the distance, estimate of the distance to v. Okay. This is what is being stored. We are storing nb u v. What is that? That is the next node on the path to v, that is also stored in u. And in addition, for every neighbor x of u, we are keeping in u an estimate the distance from x to v. So, I am keeping what is the estimate of the distance from x to v in u. Okay. Similarly, what is the distance from okay. Similarly, what is the distance from okay. So, I am, what is this actually? This is the use estimate of the table dy. Okay. What is dy? Dy is the table maintained by y, indicating y's distance, estimate of y's distance to other vertices. Ndis u y v, ndis u y w, etc. is actually use estimate of this table, and then ndis u x v, ndis u x w is use estimate of x's routing table. So, not only does it maintain its own routing table, it also maintains estimates of its neighbors routing tables. Okay? That is the only difference in the data structure as compared to what we have seen before. Now, let us see what we do in the initialization. In the initialization, for all w belonging to neighbor u, for all v belonging to v, we first set ndis u wv to be equal to n, right. Now, see, this n is actually equivalent to infinity. Why? because we have n nodes, and if we have to go by the distances, the minimum hop distances, then that can be at most n minus 1, right. So, between no pair of nodes can the distance be n. If there are n nodes in the network, then for any reachable pair of vertices, the minimum hop distance is going to be less than n. So, when we say equal to n, we are sort of saying that these are unreachable vertices. That's the initialization part. Then for all v belonging to V, we said duv equal to n, and nbuv is undefined. Okay. Du u equal to 0, nbu u equal to local, and then what does node u do? For every neighbor of u, it sends mydist u0 to w. When does the node u do this? When it comes up, when it is booted. When node u is booted, this is what it is going to do. What is it going to do? It is going to set its estimate of all distances to be equal to n, which is equivalent to infinity, and it will set the distance to itself to be equal to 0, and then just like Chandi Mishra's algorithm, it will broadcast to its neighbors that my distance from me is 0. So, u is going to broadcast my dist u is 0. Is that clear? Okay. Now, let us look at this procedure recompute V, which we will use from time to time. We will see where we use it. The motivation of doing recompute V is to see whether my distance to V has changed or not. So, recompute V will be executed by u to test whether u's distance to V has changed or not. Okay. Now, if V is equal to u, then what are we going to do? We know that this is local. So, we will set duv equal to 0 and nbuv equal to local and end. And that is the trivial case. If I am u and I am doing recompute u, that means my distance to me is what? 0, right. So, that is what this will do. Otherwise, I am not V, I am not V, I am u and u is not V. Then what is u going to do? It is going to compute d equal to 1 plus minimum of ndis u w v such that w belongs to neighbor of u. Now, what are these distances? What is this? This estimates the distance from w to v, okay, where w is a neighbor of u. So, I am trying to estimate, this is my estimate, u's estimate of the distance from w to v. Okay. So, it is going to find out that who has among my neighbors according to my estimates, which is the one which has minimum distance to v. I pick that one up, and then plus 1 is giving me my best bet of the distance to v. Now, if I find that d is less than n, then what am I going to do? I am going to set duv to equal to d, and I am going to do nbuv equal to w. Which w? The one for which 1 plus ndis u wv is equal to d. So, out of this, there is one minimum, okay, that minimum is for some w, okay, that w becomes my neighbor, because I am now going to route packets with destination V through that node W, right. Now see, this is all being done locally, everything is being done locally based on the local data structures, no messages exchanged anywhere. Okay. Now if D is not less than N, we will see the cases where this happens. Then we will say duv equal to N and NBUV equal to UDEF. What does this mean? This means that V has become unreachable from U. This part will be executed when there is no way to reach V from U. Okay. At that time we will make this undefined. Then if duv has changed, then for all x belonging to neighbor U, we will send mydist V duv to x. Now what are we doing at the end of this computation? This part of the computation actually checks whether duv changes or not. If duv changes, then this node U will inform its neighbors that my distance to V has changed and my distance to V is now duv, or the change distance. Okay. Is this recompute clear? What are we doing in the recompute V? We are simply recomputing based on local information what is the best distance to V, updating the neighbor on the path to V accordingly, and if there has been any change over whatever was duv previously, then we inform our neighbors that my distance to V has changed and this is the new distance from me to V. Clear? That is what recompute V does. Now let us see where we use recompute V. When a node U receives a mydist VD message from neighbor W, when I receive a mydist VD message from my neighbor W, this is what I do. I change ndis UWV to equal to D. Why? Because W is telling me that its distance to V has become D, right. Now where do I store that? I store that in ndis UWV, because that is where I am storing my estimates of W's distance to V. Okay. So we put that here, but now that the distance from W to V has changed, it is possible that my distance to V has also changed, possible. Okay. It is possible in two ways. One way is that maybe now my path to V will go through W, or it could be that this cost has increased and previously I was routing packets for V through W, now I may choose to route it through another neighbor because this has increased. Remember that this D may be greater than its previous value or less than its previous value. The cost may have gone down or gone up. Okay. In either case, my distance to V may have changed, so I need to do a recompute V. Okay. And if that recompute V changes my distance to V, then I will again broadcast to my neighbors that my distance to V has changed. So I will send out mydist V and the new distance to my neighbors. Okay. That is how the algorithm, that is how the wave propagates. Okay. What does a channel failure, how is it handled? When a channel fails, you remember that we assume that the neighbors, the two ends of the channel are informed about that. How are they informed about that? They are informed by virtue of this message, fail W. So, the channel informs the two nodes at its two ends that it has failed. Now, what does node U do when it receives a failed W channel, a failed W message? It takes W of its list of neighbors, because now the channel to W has failed. So, W is no longer a neighbor of U. Now, if the set of neighbors changes, then again my distance to any V can change, because previously I was routing packets maybe through that channel, through that neighbor, but that neighbor is no longer there, that channel is down. So, I will have to recompute my distances to V, right. So, for all V belonging to V, we do recompute V. Okay. Now, remember that for all V we have to do this, not for any particular V, right, because distances to any V can have changed. What do we do when channel UW is repaired? When the channel comes up once again, then the node U receives a repaired W message from the channel. That means that W is a neighbor once again. So, NeiU is now NeiU union W. W is a neighbor once again. Then what do we do? For all V belonging to V, we change NDIS UWV to equal to N. Why? Because now I have no estimate of the distances from W to V. Okay? I have no estimates of the distance from W to V. So, I set all that to N, and also I send my routing table to W. What is W going to do with this? It will update NDIS W UV with it. When this message is received by W, W will update NDIS W UV. And look, W is also going to do the same thing symmetrically on the other side. It will receive a repair U message, and it is going to send mydist W, mydist V DWV to me. So, in other words, what W is going to do is W will send its routing table to me, and then I will update these, the one that I have set to N, I will update that when I get the similar mydist messages from W, right. Then I will update NDIS UWV with that, and then I will do recompute V for all V's, and then whichever ones have changed, I will broadcast that to my neighbors. Is it clear?
Who will send the failure message? Who will send the failure message?
Who will send the failure? The failure message is going to be sent by the channel. Yeah. We assume that there is some sensor which detects that the channel is not there, and that sensor is actually sending the message up the stack. So, at the network layer, you get a message saying that this channel has failed. Okay.
Sir, this algorithm is look like a distance vector algorithm or routing.
This is based on minimum hop. We want to find out the minimum hop distances from every node U to every node V. Okay.
So, the starting point of this algorithm will be obviously for all your neighbors, you know you keep it, the distance is 1, and then you will broadcast this. How would the algorithm start as such?
Yeah, so let us look at it, let us look at some examples, right. Now, suppose at some point of time I have this node U and I have this node Z, and Z is at a distance of 3 from u, okay, all right, and then there is some at a distance 7 there is some y. Okay, let me we are going at number of hops, right? So let me just do it once again. So z has a path of length 3 to u, okay. Z has a path of 7 hops to y, okay. Then from here there is a path of 5 hops to w, all right. Now what is dy w? 5, okay. dz w is 12, right. What is du w? No, these are all bidirectional channels. So I just drew the arrows, shouldn't have drawn the arrows. So what is this? 15, right. Now let me draw the neighbors of this. Let us say that this has neighbor p on this path and neighbor q on this path, okay. So currently what is NB Z W P, okay. Now and what is let me draw this as some x. So NB U W is x. Now what happens is that this link comes up, and let us say that this link, this is one cost of 1 single hop. Now when this link comes up, at that time what happens is this one sends its routing table to u, u sends its routing table to w. What was w's routing table? dw y was 5, right. So now they exchange their tables. When they exchange their tables, then what is u going to receive? It is first going to receive my dist w 0. So from that it is going to recompute the distance to w, it is going to do a recompute w, and that is going to change this to 1, right. And what is this going to become? W, right. It is also going to get a mydist, it is also going to get a mydist y 5 message, right. What was duy previously? 10, it was 10, now it will be updated to 6, okay. what was NB uy at that previously? X. Now it will become W, right? Okay. What was dW u previously? 15. Now it will become 1. Okay. What was dy u previously? 10. Now it is going to get, this one will broadcast MyDist. When it gets this one, after updating this, it will broadcast MyDist u1. When it gets a MyDist u1 message, what will this do? This will update it to 6. See, this is how this propagates, and then this one will send MyDist W. How much has it become? 1. This is what U will send to Z. Then what is Z going to do? It will do a recompute W. When it does a recompute W, it will change this to 4 and it will change this to Q. Is it clear? That is how the information propagates, right? Yes.
You cannot send the message to Z, it will just send it to X. X will then again in turn send it to whatever.
Yeah, that is how it is going to go. That is how it will go. From U, the MyDist W1 message is going to go to X, then X will update, then it is going to go along the path, yes, not directly. Okay, all these messages are going to flow through these things. Now, is this clear? Right. Now, you see the good news that something has come up propagates very quickly, and they are updated, everybody's costs go down if at all. See, if a channel comes up, that will not increase the cost of anybody, the cost will only go down, right, and they will settle down into the best minimum hub distances once again. The problem is with the bad news. The bad news spreads in a very difficult way. To understand why that happens, let us consider this case, that I have a node U, I have a node W, and I have a node Z. Okay. Now, these are neighbors. So, in my stable state du W is 1. What is NB U W? W, right? My dz W is 2, 1 hop, 2 hop. NB Z W is U. Okay. So, that is nice. Now, this channel goes down. This channel goes down. What is U going to do? You will get a failure message. Now, you will try to see if there is any other path through its neighbors to reach W, right. So, what is it going to look at? Okay, what is it is going to look at what is NDIS U Z to W. So, that is 2, right. What is recompute W going to do at U? It is going to look at the minimum of this NDIS plus 1. What is NDIS after the failure has been discovered? What is see it is going to look at only the neighbors, right. So, W is no longer a neighbor. So, W does not count. So, what is it going to do? It will revise, recompute W at U, will revise this one to 2, and it will to 3, yes, 2 plus 1, so 3, and it will revise this to Z. What will it then do? It will send a MyDist W 3 message to Z, right. What is Z going to do? It will update NDIS Z U W to 3, right. Previously this was 1, now it will be updated to 3 because it receives, because U is now telling that its distance to W has become 3, right. What will this one, what will Z now do? It will again do a recompute W. What will the recompute W do? Set this to 3 plus 1, 4, and it will set this to U only, right, because it does not have any other neighbor. And then what is it going to do? It will send a MyDist W 4 message to U. What will you do? Update this to 4, and then update this to 5, and then send a this will continue. Why is this happening? This is happening because each of U and Z is thinking that there is another path through the other. U is thinking that there is another path through Z, Z is thinking there is another path through U, right, and therefore they are just counting to infinity. They are just going to go from 3 to 4, 4 to 5. I am saying that no, my cost, so you said you can reach W in 5 steps, then I can reach in 6 steps. Then you said that, oh, you can reach in 6 steps, then I can reach in 7 steps, because I go through you. And then I say that, okay, you can reach in 7 steps, then I can reach in 8 steps. Then he says that, okay, you can reach in 8 steps, then I can reach in 9 steps, right. So, in this way they keep on counting to infinity, right. So, we need to keep a check that we do not keep on counting, because then we will never terminate, okay. That is why we assume that we know the number of nodes in the network, we know n. So, we know that this count can never become greater than or equal to n. That is why you will see in the algorithm, you will see that if this is one case, right, if d is less than n, if we find that d has become equal to n, which is what will happen as you keep on counting, at some point of time d will become equal to n. When it becomes equal to n, we do not count any further, we simply set duv equal to n and nbuv equal to undefined. okay, right. That is where it stops, this exchange will stop there, because the moment your distance reaches n, you know that actually you are counting, there is no real path. So then you will say that V has become unreachable. So in our case W has become unreachable. Then this one will you will set NB U W to be equal to undefined. Is it clear? So the good news spreads easily, that the algorithm automatically converges. For the bad news, we keep counting until n, assuming that we know the number n. If you do not know the number n, we will have to use some upper bound on n, and then once we reach that upper bound, we stop the exchanges at that point of time. Okay, all right. Now that is about what we have to discuss in the net change algorithm. There are a few other topics that we need to touch upon. The first of these topics is that in reality we have to follow some more structure so that the routing tables are compact, right. So in other words, we need to have the following kind of property to have compact routing tables, that is that we define what is called a cyclic interval. Okay. So what we want is, in simple terms, that if I have a node, I have a set of neighbors, there are certain nodes that I will be able to reach along through this neighbor, certain nodes I will be able to reach through this neighbor, certain nodes I will be able to reach through these neighbors, right. Now I want that all the nodes that are there here lies in some cyclic interval. What is a cyclic interval? A cyclic interval can be defined like this, that a cyclic interval AB is A plus 1 to B minus 1 if A less than B, okay, and it is equal to 0 if so if A is less than B, then this cyclic interval is the set of numbers from A to B minus 1. If A is greater than or equal to B, then it is actually the numbers from 0 through B minus 1 and then from A through N minus 1. So are you getting what this means? This means that we have all the numbers from 0 through N minus 1, okay. Now if I choose for example 5, 10, then it talks about this interval, and the interval 10, 5 is this remaining set of numbers, right. Now what that essentially means is that I want that all the nodes in this should be in one interval. So suppose this is between A and B, okay, this is between B and C, and this is between C and A. So all nodes having numbers addresses between A and B will be here, all nodes having addresses between B and C will be here, and all the remaining nodes will be here. Why do we want this kind of an interval? Because then we know that if the address is within this range, then this becomes the next node. if the address is within this range, then this becomes the next node. If the addresses are within this range, then this becomes the next node, right. Now, if you can partition if you can number the nodes in such a way that for every node this holds, then we can have compact routing tables in every node, because we know that for this interval those addresses can be reached along this node, for this set of addresses this node, not for for each individual addresses we are not storing which is the next node, we are storing for this set of addresses this is the next node, for this set of addresses this is the next node, right. Can you think of a way to number the nodes in a tree such that this property holds, that at every node the nodes that can be reached along the neighbors form a cyclic interval, okay. Think of this as an exercise, that given a tree I want to number the nodes or assign addresses to the nodes in such a way that for each node the following property holds, that if I look at the nodes that are reachable along a neighbor, it is given by a cyclic interval, okay. Now, if we could do that, then that's nice. We actually, when we assign addresses to the nodes in the internet, we actually do that and a little better than that. We not only want to make sure that they are in a cyclic interval, we also want to make sure that I can create a network mask. So, I can say that for this set of, if the leading bits are this, then all nodes in the internet which have the leading bits as this can be reached along this neighbor, okay. So, that is also a cyclic interval, because I am saying that all nodes which start with 144.16 and then XX XX, these are reachable along this neighbor. What does this set of addresses indicate? It is a cyclic interval. In addition, it also makes sure that that you can represent this set of addresses by using only one set of bits, right. Now, we do the numbering of the addresses in the internet in such a way that for every node you can create those masks, right. Now, within your network also, when we create masks for the different departments, we have to be careful that we allocate these addresses in such a way that this property holds, right. That way the routing tables remain compact, okay. I have a few additional things to talk about in this routing, but that is not going to constitute a full lecture, right. So, one of these days I will take out some time and we will just have a discussion on some of these additional topics on routing, but more or less whatever is the main thing is already has been discussed.